Good morning, ladies and gentlemen. First of all, I would like to express my thanks for giving me this opportunity to be here. I'm Luís Laim and I'm working as a PhD researcher at the University of Coimbra in Portugal. I'm going to present to you an experimental work developed in University of Coimbra over the last years in collaboration with many professors and researchers, including Elder Craveiro and Professor Simoes. This study concerns an experimental investigation into the structural fire behavior of restrained cold-form steel columns with stiffened and unstiffened sections. So the main objective of this research work was to evaluate the fire resistance of single and built-up restrained cold-form steel columns in compression with intermediate and edge stiffeners based on results of an extensive campaign of experimental tests over the last years. To accomplish this goal, transient state axial compression tests were first carried out in order to assess mainly the failure modes and the critical temperature of the studied column. Secondly, the effect of cross-section shape, web and edge stiffener configurations, slenderness, and stiffness of the surrounding structure to the thermal elongation of such columns have been investigated. And finally, some recommendations and suggestions will be given for future construction applications and design rules based on such results. Keeping all this in mind, unstiffened and stiffened sections were selected for this study, including plane channels, lip channel, sigma, and sigma plus profiles. Plane and lip channel profiles were fabricated with S280GD structural steel, whereas sections with intermediate web stiffeners, including Sigma and Sigma Plus, were fabricated with S320GD structural steel, in order to take advantage of the maximum effective area of such sections. Built-up sections were also tested, as it can be seen in this figure. All profiles were 2.5 mm thick, their length was about 3 meters, and the spacing of the fasteners along the column length was 725 mm in the maximum. This figure illustrates a general view of the experimental system used in the fire resistance tests of cold-form steel columns. Briefly, this test setup consisted essentially of a two-dimensional reaction frame, a three-dimensional restraining frame, a hydraulic jack, two load cells, and a modular electric furnace. The hydraulic jack was hung up on the two-dimensional reaction frame in order to apply a serviceability load of the tested columns, and it was controlled by a servo-hydraulic central unit. The three-dimensional restraining frame was used to take into account the stiffness of the surrounding structure to the thermal elongation of the tested column. These fire tests were performed in two stages, loading and heating stage. Firstly, the specimens were loaded up to the target force under load control. The load level applied on the columns was 50% of the design value of the load-bearing capacity of the respective columns at ambient temperature, calculated in accordance with the methods proposed in Eurocode 3. Afterwards, the column was exposed on all four sides to high temperatures in such a way that the average temperature in the furnace followed as close as possible the ISO 834 standard fire curve. As results of this investigation, it is shown here as example the temperature evolution on a cross-section of the 2C column and along its height. It was observed that the temperatures across the cross-sections were fully uniform for single columns and partially uniform for built-up cross-sections. In other words, some differences in temperatures were observed between the non-overlapping and overlapping regions. The maximum temperature difference was about 100 degrees Celsius. From the collected data of the experimental tests, it was checked that different critical temperatures were obtained under identical conditions, including design load level, thermal action, and boundary conditions. For example, the difference in the critical temperatures reached in the maximum 194 degrees Celsius between 284 and 478 degrees Celsius for the pin-ended 2C column and the semi-rigid-ended C column, respectively, which is a tremendous difference. From previous investigations, it is known that the actual restraint to the thermal elongation of the columns may significantly affect their critical temperatures, but it was not the case for this study. Note that it is only expected that the restraint has significant influence on the fire resistance of restrained columns when the actual restraint ratios are lower than 5%, as it can be seen in these figures, for example. And the minimum actual restraint ratio was about 7.5% for the 2R columns in this study. However, the actual load level applied on the columns may be another story. The actual serviceability load was not always the same for all columns as it was desirable. From experimental tests at ambient temperature, it was checked that 50% of the design load level applied on the C2CR and 2R columns in fire conditions did not correspond with 50% of their load-bearing capacity. As it can be seen in this figure 6, the actual initial applied load was only 30% of the respective maximum load-bearing capacity for the semi-rigid-ended C column, and by contrasting, it was 50% for the semi-rigid-ended 2R column. It is evident that the higher actual load level, the lower the critical temperature is. However, it seems that the 2C columns were an exception, which may indicate that the overlapping regions and the shear deformations at their boundary conditions may play a crucial role at high temperatures. Additionally, the critical temperatures of the pin-ended built-up columns were also lower than those of semi-rigid-ended columns for the same actual load level, since the higher the slenderness ratio, the higher the shear deformation effect is for the same screw spacing. Nevertheless, the critical temperature of the pin-ended R columns was higher than that of the semi-rigid-ended R columns with C and U profiles. This may be due to the fact that such columns are asymmetric about the minor axes of their cross-section, which may result in different directions of their flexural buckling failure modes. In other words, it was observed that the highest compression stresses occur in the web of U profiles for the pin-ended R columns, whereas the highest compression stresses mostly occur in the web of C profiles for the semi-rigid-ended R column. Note that when the highest compression stresses occur in the web of the C profile, the contribution of the U flanges are practically neglected comparing to the lip flange junction of the C profile, when the highest compression stresses occur in the web of the U profile. This effect still becomes higher at high temperatures than at ambient temperature, since the lip flange junction of the C profile is more protected from the radiation than the flanges of the U profile. More evidence about the collapse of single and built-up cool-form steel columns can be collected from actual restraining force results generated in the columns during heating. It is known that during heating up, the actual restraining force in columns increase, and eventually at a certain time they will reach their buckling resistance load. Then the actual restraining force starts to decrease, and when a significant degradation of the mechanical properties of steel occurs, the column may fail. The column no longer can support its initial applied service load. In general, the lower the actual load level, the higher the maximum relative actual restraining force generated in the column is, as expected. The higher the buckling temperature, the lower the post-buckling strength of the columns is for the same actual load level. So the post-buckling strength of built-up columns decreases with increasing their slenderness and with increasing buckling temperature. It was observed that the semi-rigid-ended single columns with C, sigma, sigma plus sections had the highest maximum relative actual restraining force contrasting with the pin-ended built-up columns with 2C, 2 sigma and 2 sigma plus sections, which had the lowest relative actual restraining force, as it can be seen in the figure on the left side, leading respectively to the highest and lowest critical temperature of such columns, as it can be seen in the figure on the right side. Once more, the actual load level and the composite action effect play an important role in the structural fire behavior of such columns. Finally, in conclusion, it was first observed that the overlapping regions, composite action, number of stiffeners, section geometry, and design load level play a crucial role in the structural fire behavior of such columns. In addition, inadequate design rules at ambient temperature for built-up cold-formed steel columns might have a negative impact on the actual fire response of such members, leading to lower critical temperatures than expected. On the other hand, it is also suggested that the shift of the geometric center between full and effective cross-section should not be considered for the fire design purposes when it is calculated the design buckling resistance of the compression member at ambient temperature. It is also not recommended the use of asymmetric built-up cold-formed steel sections. Such sections can be very prone to their imperfections, which may lead to an underestimated design buckling resistance of the member at ambient temperature, and consequently to low critical temperatures in fire situations. Lastly, columns with stiffened sections, especially with double-edged fold stiffeners, might have an enhanced fire behavior for high load levels, higher than 50%, since the effect of cold work of forming might not yet be completely compromised for such critical temperatures, when such temperature is lower than 400 degrees Celsius. Further information about this topic presented here today can be still found in this relevant list of references. Okay, I've already finished my presentation, and so I'd just like to thank you all for your attention. Many thanks. It has been a great pleasure to be present here today. Bye-bye.